Module 21, we have a little more applications of these exponential growth, and there's only 4 topics here. So we're going to start with writing and evaluating a function, modeling continuous exponential growth or decay, given doubling time if it's growth or half-life if it's decay. Okay, and notice that we have continuous exponential growth. So we're going to go back to our, here, let's go to A equals PE to the RT. We're changing that up to Y equals Y naught E to the RT. Okay. So the first example, we've got one with a half-life. So we have a specific radioactive substance follows a continuous exponential decay model. Okay, so that's what we've got here. Its half-life is 7 hours. At the start of the experiment, 537.2 grams is present. Okay, so if we're going to model this, we need to know we need Y naught and we need R. Okay, Y and T are our variables. Y naught and R are constants. So all we're going to do here is plug in what's given to us so that we can solve for R, because we already have Y naught. Okay, and so what we can do here is, 537.2 will equal E to the R times 7. 7 is the half-life. So over here, I'm going to put half of 537.2, which, spoiler alert, it doesn't really even matter. I don't even care what go ahead and use your calculator and find what half of it is. But the first thing you're going to do is divide, right? So, go ahead and put it comes out to be, I don't even know. Here. 537.2 divided by 537.2 divided by 2. Okay, take your time and figure out that that's 268.6. But then no, right away you're going to divide anyways, and you're going to have 1/2, right? If 268.6 is half of 537.2, then 268.6 divided by 537.2 is going to be 1/2. Okay, so it doesn't really matter. Okay, we could figure out the rate without that 537.2. Okay, so we're going to do the natural log of 0.5 equals the natural log of e to the 7r, which remember allows that 7r times the natural log of e, which is 1. So r is the natural log of 0.5 divided by 7. Okay, so our model is y equals 537.2 e to the natural log of 0.5 over 7 t. Okay, and I'm even going to tell you a little trick here. It's always going to be the natural log of 1/2 divided by the half-life. Natural log of 1/2 divided by the half-life. Okay, and this is the answer that Alex is going to take, and it's going to be fine with it. One thing that you could do is e to the natural log of 0.5 divided by 7 times t. We can rewrite that as e to the natural log of 0.5 times t over 7. E to the natural log of 0.5, they kind of undo themselves, and it's actually just 1/2. So another form, and you can see if maybe Alex will take this too. Y equals 537.2 e to the natural log of 0.5 over 7 times t is equivalent to 537.2 0.5 to the t over 7, if you want to do that. Okay. But then the part B says find the amount present in 13 hours. So just plug 13 in. Okay, so for part B, how much after 13 hours? We're going to have 537.2, 0.5 to the 13 over 7. Okay, and they're going to let you use your calculator for that, and we should get 148.3 grams. Okay, Let me see if they have a doubling one here, because that was the half-life, and they also said they'll have doubling. Okay. This next one, we have the area covered by a certain population of bacteria. Okay. So you have bacteria. It tells us that it is continuous exponential growth. Okay, and it says suppose that a sample culture has an initial area of 7.6 millimeters squared. Okay, so they said that's the initial area, so you figure out that's why not. And it doubles every 5 days. Okay, so y equals y naught e to the RT still. Okay, and then we'll have that whole doubling thing. Well, here we know that y naught is going to be 7.6. So again, like I was saying before, it doubles every 5 days. So go ahead and figure out what twice 7.6 is. You really don't need to. 2 equals 1 e to the 5r. Yeah, because t would be 5. Okay, so 2 equals e to the 5r. The natural log of 2 is the natural log of e to the 5r. So that's 5r natural log of e, which is 1. And solving for r, it's the natural log of 2 over 5. Okay, so just like for the half-life, r is the natural log of 1/2 over 2. When we're doubling, it's the natural log, natural log of 1/2 over whatever the half-life is. When we're doubling, it's the natural log of 2 over whatever the doubling time is. Okay, so our equation there is just going to be y equals y naught e to the natural log of 2 over 5 times t. And just like the previous one, you can write that as 7.6. E to the natural log of 2 is just 2 to the t over 5. Okay, and then for part B, it says find the area in 18 days. So we're just going to plug 18 into that. So that comes out to be about 92.2 millimeters squared. Okay. All right, next one. We have comparing linear, polynomial, and exponential functions. Okay, so this one says compare the functions. F of x is 2x cubed, and g of x is 2 to the x by completing a table and this little inequality. So first they give you a table. So we have x, f of x, and g of x. Okay. And it does say you can use the calculator on Alex if you want. They do give you for 5, f of x is 250, and g of x 2 to the 5th is 32. Okay. And then they ask you to fill in the table. So they give you 6, 11, 12, and 13. Okay, so you're just going to take your time and do those calculations. 2 times 6 to the 3rd power, and then 2 to the 6th, so we'll have 432 and 64. And then for 11, we'll have 2,662 when you do the right calculation, and 2,048. And then we'll have 3,456 and 4,096. And then finally, 4,394 and 8,192. Okay. And then they ask for x greater than or equal to 6. The table suggests f of x is blank greater than g of x. And you fill in that blank with either, this is kind of weird how it's set up. Let me see. I feel like greater than should be the blank. Okay, sometimes. Okay. Yes. So it must be always, sometimes, always, or never. I can't see the options right now. Okay. So f of x is greater, f of x is greater, f of x is greater, g of x is greater, g of x is greater. Okay. So f of x is sometimes greater than g of x. So one thing that's nice about this one too, and I would encourage you to just graph those two functions and see, somewhere between 11 and 12, they're crossing, right? F of x is on top for a while. They kind of, let's see, f of x looks like this, and then g of x looks like that. And at some point between 11 and 12, they cross each other. Okay. So that's all you're doing with those. I don't think you need another example for that. So let me know if you do need another example, but there you go. The next one is identifying linear, quadratic, and exponential functions given ordered pairs. Okay, so if it is linear, well, here, if it's linear, we know that it has like a constant slope. Okay, so if the first differences are equal, okay, so, and I think they're going to have you go up by a constant amount. Okay, so if it's linear, the first, and I'll show you what this means, first differences are equal. If it's quadratic, the second differences are equal. And if it's exponential, the ratios are equal. Okay, so function one that they give you, x, y, 3, 4, 5, 6, 7. Just make sure those are going up just by 1. And 71, 45, 25, 11, 3. Okay, so you can see as we go up by 1, we can check our differences. So 71 to 45, it's going to be negative. This is minus 26. 25 minus 45, that's minus 20. So it's not linear. Okay, 11 minus 25, that's negative 14. And 3 minus 11, that's negative 8. Okay, so our first differences are not the same, but you can kind of tell your second differences are. Negative 26 to 20, that's plus 6. Negative 20 to negative 14, that's plus 6. Negative 14 to negative 8, that's plus 6. Okay, so here's your first differences. Here's your second differences. Those are the ones that are equal. So this is quadratic. This is a parabola. Okay. Function 2. 0, 1, 2, 3, 4, and 6, 18, 54, 162, 486. I can already kind of tell by how quickly it starts to increase that it's probably exponential, but we'll just double check anyways. 6 to 18 is plus 12. 18 to 54, that's plus 36. 54 to 162, that's plus 108. And then 486 minus 162, that's plus 324. So first difference is not the same. Second difference is I have a plus 24, and then 108 minus 36, I have a plus 72, and then 324 minus 108, that's plus 216. Okay, so it's not quadratic either. And then fun fact, if like the third differences were the same, then it would be a cubic function. Okay, if the fourth differences were the same, then it would be a to the fourth power, fourth degree function. All right, so it's not quadratic, it's not linear. Now we're going to check to see if it's exponential. Okay, I'm going to switch colors here. So 16 to 8, that's times 3. 54 divided by 18 is also times 3. 54 times 3 gets me 162, and 162 times 3 gets me 486. So we have these constant ratios, a constant multiplier between terms. So this is exponential. Okay. And then I have function 3. Okay. So this one again, let's figure out, this would be minus 10, minus 6, minus 2, plus 2. So definitely not linear. The fact that it goes down and then back up tells you it's definitely not a line. This would be plus 4. This would be plus 4. This would be plus 4. So we have quadratic here. Okay. So that's how you do those. All right. Our last topic of this whole unit. We have solving an exponential equation. So this is kind of similar to what we saw in Module 20 by finding common bases and not just linear exponents, linear and quadratic exponents. Okay, so this one we have 2 to the x squared plus 8x plus 3 equals 16 to the x plus 2. So again, if you remember Module 20, if you don't, you might want to go back and look at it. Okay, we can write 16 is 2 to the 4th. Okay, so that is the same as 2 to the 4x plus 8. So now we just have to figure out when does x squared plus 8x plus 3 equal 4x plus 8. And it's just a nice little quadratic, right? Get everything on the same side. Factor it. So we'd have an x plus 5 and an x minus 1. And then solve. X is either 1 or negative 5. So similar to what you've already seen before. Okay? All right, that's it then.